Lester, Wushu Engineer. This will be the last video that I upload for 2023. So I'd like to wish you all a very Merry Christmas and a happy and productive New Year. Hope you're all safe and have a great time. We've recently been snowed under quite drastically with the scientific study that we are currently performing in collaboration with the University of Southern Queensland. But despite the ridiculous amount of work that still remains to be done, the results to date are looking extremely promising indeed. We seem to be achieving not only statistical significance, but are in fact demonstrating some very, very bold results, and very exciting results too. So I look forward to reporting on that study on my channel once we have recruited the last of our willing participants next year and completed the data analysis. I'm a big fan of science fiction. You don't need to be a rocket scientist to realize that based on the content I put up on my channel, as well as fantasy, of course. And science fiction is full of imaginative solutions to future armor technology. The approaches to armor technology featured in various sci-fi books and movies range all the way from the high-tech esoterica of the force field, as showcased in the Dune series, to the massive monolithic ceramite and plasteel plate armor of the Warhammer 40k Space Marines. Now, I'm not going to get into talking about force fields in any detail in this video. I absolutely love the idea of force fields, but I cannot yet see any practical way that this kind of armor can be achieved without some kind of magic MacGuffin technology being developed that's not yet been developed. I'm sure you guys will post up some links to science articles about various takes on force fields and the like. I do appreciate the information, and there's almost certainly articles out there that I have missed. But do remember that I am also eagerly looking for and reading these articles in the hopes that force field armor can be developed. Force fields seem to be a little like a stable, practical nuclear fusion power generation. Always 50 years away. Now, most of the experiments that have been eagerly presented by science news outlets as a basis for future force field technology are typically performed on very, very, very tiny scales and involve very, very, very expensive equipment, and they generate typically very, very, very small effects. Certainly, nothing that I have seen is a basis for a robust force field technology that could be developed quickly and that could turn aside or stop high velocity projectiles. However, in some of the more practical science fiction visions of the future, armor is described as reacting to incoming energy in various ways, often by stiffening to distribute impact energy over a larger surface area. I usually refer to this kind of armor as reactive armor, in that it reacts to incoming attack stimulus in some way. And typically it'll be passive reactive armor. There are such things as active reactive armor systems that actually require energy in order to perform the role that they play in diverting or stopping incoming projectiles, and those kinds of systems are often seen actually deployed on tanks. Probably the most famous example of that is the use of high explosives to essentially disrupt a penetrating projectile. Another example actually involves the use of very high sort of electrodes, high voltage, high current electrodes separated by a dielectric, and their job essentially is to disrupt the projectile as it's penetrating the armor. As it penetrates the two plates, it completes the circuit and essentially destroys that projectile, or at least damages it significantly on the way in, disrupting its ability to penetrate the armor. So those are really interesting designs, but those are more active reactive systems. Now, in my last video, I did some very promising tests of stab-resistant armor made using 4 layers of ultra-high molecular weight polyethylene unidirectional plastic sheet bonded together with silicone adhesive. This armor performed incredibly well when compared with other types of budget, low-profile, flexible, stab-resistant armors on the market. However, one of the potential problems using this kind of low-profile, flexible sheet is really a problem that you would encounter with any type of thin, flexible, stab-resistant armor, in that while the knife blade did not penetrate the armor effectively, the armor still bunched up around the knife blade, wrapped around the knife blade at the point of impact, allowing the knife blade to still cause a lot of localized point blunt force trauma, even though it did not cut into the target. And so in that video I suggested that one potential solution would be to make the armor reactive in some way, to stiffen under impact. I suggested incorporating shear thickening fluids or shear stiffening elastomers in the armor construction. Now, while I'm talking about that, one of my viewers commented about an actual real-world incident involving the use of this kind of reactive gel-based armor. I believe I have heard similar second-hand stories about this incident, but on searching for it, I couldn't actually find any record of it in any kind of news media or anything like that, actually. So, mate, if you've got a link to anything, any kind of record of that incident, I would really appreciate it if you could share it. I am interested in following up on that. I'd like to look into the full details of the event, because to my knowledge, while many prototypes of reactive body armor have been trialed and are in development, there does not appear to be any real legitimate mature instance of this technology on the market and in use. A lot of manufacturers claim to be using these kinds of systems, but on close inspection, it's almost like the old adage about steampunk. You know, all you need to do is to slap some gears on it, and then you can call it steampunk. In this case, all you need to do is to throw some quote-unquote shear thickening fluid into the armor, and you can call it modern reactive armor, when its performance is not dependent on that. It's literally just made of typical brute force approach to armoring, which is quite common in the industry today, which is literally just put as many slabs and slices of material in front of the projectile as you can and hope for the best. So I would appreciate any information about this particular event and system so that I can follow up on it for my channel. Now, while I'm talking about viewer comments, another of my viewers commented on my dismissive attitude towards Bilbo Baggins wearing his mithril mail armor and being stabbed by the cave troll. And I must make a bit of an apology about that. I have to admit that I did not do the topic proper justice in that video, because it wasn't the main subject of the video. I wasn't really doing an analysis of how mail armor reacts to incoming force. So the long and the short of it is that yes, mail armor would likely show a reduction in penetrative point impact force over a lighter fabric with the same tensile strength, simply due to the mass of the discrete links in the mail and the way that force is dispersed through the links of the mail armor. However, this reduction would not be as great as some may assume. Male armor suffered historically from a basic weakness in dealing with point impacts, as evidenced in many contemporary tests on YouTube showing knife and arrow penetration of historically accurate male samples, as well as in the historic evolution of plate armor to counteract those kinds of point impact threats. But what I must mention in connection with this comment is the relatively recent development of reactive metallic male armor. Recently, scientists at Singapore's Nanyang Technological University and Caltech in the US developed a type of reactive male armor that stiffens under impact. It's made of specially designed 3D printed segments that interlock and become a more unified structure under rapidly applied impact forces. Now, while the famed dwarven smiths of Middle Earth did not have access to 3D printers, they were certainly long-lived master craftsmen, even rivaling the elves in some regards, who could have conceivably invented a similar type of male armor and incorporated it into Bilbo's mithril male shirt. So I'll have to give Frodo a pass on the cave troll stabbing incident under the assumption that Bilbo's mithril male vest, which he was wearing at the time, was reactive and did stiffen under that kind of impact. Because if it wasn't, he would have undoubtedly died from broken bones, possibly a ruptured spine, burst internal organs, and severe internal hemorrhaging just through the sheer point impact force behind the cave troll wielded spear. Anyway, on with the video. I went away and I researched, experimented, built stuff, and thought about things for a while, and generally did the kind of things that I do behind the scenes. And now I'm back to demonstrate a proof of concept, showing that this approach can perhaps lead to a very practical and workable solution for stab-resistant armor. Firstly, this video is going to be a bit different to my normal videos in that in my normal videos, I'm usually completely transparent about what I did in a video and how I did it. I'm not going to be completely transparent in this video about how I did what I did in this video, because I own a patent for a special reactive ballistic protection system, which I'm still actively developing. And in designing this reactive stab resistant armor, I referenced one of the concepts that I have incorporated into my patented design in order to develop the reactive elements of the stab resistant reactive armor system. So in the interests of ensuring that I'm not revealing any kind of IP in this video, any kind of sensitive IP in this video, I will just not be explaining exactly what I did and how I did it. However, just for the record, the reference that I made to my patented design is very small and almost inconsequential. But you can't be too careful with IP, and that especially IP that's actively being developed. And so my apologies to those who are interested in exactly what I did to make this. I'll not be revealing that information. So, this video, as I said, is merely a video demonstrating a proof of concept. There are, of course, many other publicly accessible designs for reactive materials out there, such as shear thickening fluids and some shear stiffening elastomers that could be incorporated into the ultra-high molecular weight polyethylene unidirectional sheets to make it function in a similar way to what I demonstrate in this video. So anyway, I developed a shear stiffening elastomer, or SSE, that I chose to call Salmon Snot, which I used to bond the layers of ultra-high molecular weight polyethylene unidirectional plastic sheet together. What is an SSE, or shear stiffening elastomer, I hear you ask? Well, although there is some research directed at shear stiffening elastomers, there's certainly not quite as much current research directed towards them as has been directed to developing shear thickening fluids, also referred to as dilatants or non-Newtonian fluids. So there's no dedicated Wikipedia entry that I can just slap up on the screen. But basically an SSE is kind of like a semi-solid version of a dilatant fluid. It's typically a soft rubber that stiffens under rapid impact or high frequency mechanical stimulus to become a harder rubber. It doesn't flow like a shear thickening fluid because it's not actually a fluid, it's more like a gel or a soft rubber. This makes it actually a lot more practical for applications involving armor. You don't want your reactive components slowly leaking out of the armor or being affected by gravity, as liquids tend to be over time. Even non-Newtonian fluids over time, given time, do respond like other fluids do and collect or flow. As I mentioned before, I'm not going to reveal exactly how I made the Salmon Snot, simply because it leans too heavily on the principles, or one of the principles of my patented ballistic armor design. But this is what the Salmon Snot looks like. Okay, now I hope this I hope the camera stays in focus while I'm busy doing various things here. I'm trying the zoom function, so hopefully it works. I wanted to just show you these two pieces of the Salmon Snot material. This was actually the very first piece that I made, and subsequently, I made the armor samples that we'll be testing in this video with another mix that didn't quite match the performance of this original piece. And then I made another one in an attempt to try and figure out what the ideal ratio was. And this one is closer to what I want, but it's also probably a little bit out. But I wanted to just show you how strangely this material behaves. These samples I'm not sure whether to class them as a shear stiffening elastomer or whether they're some form of gel or what have you. But first of all, they're quite soft and squishy. So if I squash it like this, you'll see that it gets squished. I can pull it out of shape like that, and it stays that way for a bit, but over time it moves back to its original shape. So it has a bit of shape memory. If I strike it, I don't know if you can see that, it behaves like a, I don't want to drop this because it's going to jump all over the place and then I have to go and fetch it. But it behaves when struck with an impact force, so a rapid change in force, it behaves like a rubber. So if I wasn't sure about whether it was a gel or whether it was a elastomer, I would be saying this is a shear stiffening elastomer. So its mechanical properties change depending on the frequency of the applied force, or how quickly that force is applied. If I apply it slowly, it deforms easily. If I apply it quickly, then it behaves more like a rubber, or at least it behaves more like an elastomer. it has other properties as well that are really quite interesting. So I'm going to demonstrate with this little piece. Hopefully you'll be able to see this. I'm just going to snip it here with the scissors, and then I'm going to hold the ends together. A little bit of time, and then I'm going to try and pull it apart there. And you'll notice that for all intents and purposes, it's essentially become a continuous piece again. So it has self-healing properties, which is very cool. And yeah, just as for the other sample, it behaves as a rubber, as an elastomer when struck. So I think this is I think this is really cool, and possibly a very good foundation for an armor system. The Salmon Snot, with self-healing properties, it shear stiffening, behaves a bit like a fluid, a bit like a gel, a bit like an elastomer. Yeah. So anyway, I just wanted to introduce that because I think it's actually really quite cool. And you know, most sci-fi that introduce body armor of the future, most sci-fi stories or movies or what have you, have some kind of like self-healing properties. The armor has self-healing properties, and it stiffens under impact. That's just precisely what this is doing. So leveraging this, finding a way of actually making this work effectively in like modern body armor would be quite an interesting project. Anyway. Now, in order to test the capabilities of the SSE Salmon Snot reactive armor samples, I had to adapt the existing Pendulum stab test rig since we were wanting to test purely for backface signature, not stab resistance in this video. So when we're doing scientific investigations, we typically want to reduce the number of variables. So and do things step by step. So to reduce the number of variables, try to make it just one variable that you're testing, test that, and then you can build on that, on those results. So in this case, all we were looking at was backface signature. So this is what I did to the Pendulum test rig. So I thought before I show you the tests or discuss any results or actually even the materials that I'm testing here, I thought I would just explain to you the changes in the Pendulum test apparatus that I usually use to test stab-proof or supposedly stab-proof armor. So instead of first of all of the tests that I'm performing in this video are all done at 45 degrees. So it's standardized 45 degrees. In addition, because we're not actually testing stab resistance here, but actually testing the ability of the armor samples to react to rapid incoming forces, so impact forces, to essentially reduce what's sometimes referred to in ballistics tests as backface signature. Because we're just looking at that, we don't need a knife blade on the Pendulum. So the Pendulum's threat rating has dropped significantly for this set of tests, only because we only want to look at one variable at a time as far as possible. So in this case, we're just looking at the armor's ability to reduce backface signature. That's all. So instead of a knife blade, what I have here is essentially just a bar. I just happen to have an offcut of titanium because, you know, I love titanium, and I have a couple of offcuts of it. It is in total about 15 centimeters long. 7.5 centimeters project past the wooden support block here, and its dimensions when looking straight on are 0.7 centimeters thick, so about 7 mils thick, and 1.4 centimeters wide this way. So those are the dimensions. It's sort of semi-rounded off at the end, but not that much. As I said, I just had it lying around, so I decided to use this. And because it's standardized across all tests, it's not that important because all the samples will be tested with exactly the same bar. So anyway, instead of a knife blade, we've got this. Instead of a pad of foam, what we're using, because we want to be able to check the depth of the backface signature, I have a clay backing cylinder, you could say. So it's essentially just a PVC pipe with an end cap on it, or a bit of PVC pipe with an end cap on it, and it's stuffed full of plasticine. So I'm just using plasticine here. I'm not using any kind of fancy ballistic clay or anything like that, because we don't need to, because this is standardized across all tests. I'm not comparing it with other results. I'm just comparing results within this set of tests. So I've just decided to use plasticine because I had some lying around. It is 4.7 centimeters deep. So it's a cylinder of 4.7 centimeters deep plasticine clay. So that's so all the armour samples are just going to be mounted flat onto this this cylinder, and then the pendulum test apparatus is going to be lifted up with 5 kilograms on the end of it, as per normal, to 45 degrees, and this is going to come and hit the armour sample, and it will deform, permanently deform the plasticine, or at least semi-permanently, until I put it back to the way that it was, so that I can measure the depth of that backface signature. And I'm going to be measuring the depth from the original 4.7 centimeter height here. So what I'll do is I'll move the clay out of the way on the sides in case it's bulging up, and then I'm going to measure from the edges of the cylinder down to the lowest point of the divot left behind, or the donga left behind by this thing. I suppose I'd better show you what I'm using to gauge that depth. Let me get it quickly. I'll edit this section out. Okay, so this piece of high-tech equipment is what I'm using to gauge the depth. I just have a glass fiber rod which has been threaded through some corrugated plastic sheet, and I can adjust the depth of the one end of the glass fiber rod to match the depth of the penetration, and then it stays there, and then all I need to do is to measure here. And so clearing the clay on either side allows me to line this up exactly with the edges of the cylinder so that I get an accurate depth of backface signature every time. Yeah, very high tech. I know it gets the job done. That's what's important here. For the tests, I made several test pieces so that I could do side-by-side comparisons of the results. I made one test piece with 4 layers of loose, unbonded, ultra-high molecular weight polyethylene unidirectional plastic sheet, one with 4 layers of UD sheet bonded with silicon adhesive, one with 4 layers of UD sheet bonded with Salmon Snot, 2 test pieces with 4 layers of UD sheet bonded with Salmon Snot containing other mystery ingredients, and 2 test pieces with 4 layers of UD sheet bonded with a different shear stiffening elastomer. And ultimately this is what those tests looked like, followed by the results and discussion. Okay, so I'm just going to discuss the results of that series of tests that I just did. I'm going to have the results up in on a table so that you can have a look at them in terms of backface signature depth. But I felt that I actually needed to show you what some of these samples looked like, and hopefully it'll come through in this video. Bearing in mind that there are a whole bunch of caveats here. So first of all, I only did one test per sample. Okay, this is a YouTube video, right? I'm not building this for some big company or what have you, so I don't have the time or the energy to like do 100 tests and confirm all of this stuff. However, I believe that the tests are still valid, even though they're prone to error because we've only got one test per sample. But it is still interesting, especially if you have a look at the samples and how they reacted afterwards. The other caveat that needs to be inserted is that I made all of these things by hand, including the Salmon Snot material, and there are inconsistencies there. So there are inconsistencies in the way that I made these various samples. So there are inconsistencies. The other thing that we need to acknowledge is that because I made these by hand, perhaps the thicknesses of the interspersed material, so whether it's silicon or whether it's the salmon snot or whatever it is, that the thickness of those layers might differ from one sample to another because it's just done by hand. So with all of those caveats out of the way, let's have a look at the results. So first of all, without any sample on the plasticine backing disc, or the cylinder, I should say, the penetration depth was 4.7 centimeters, which is no surprise. So in other words, the probe or the bar just went right down to the base of the cylinder. That's as expected. When I used 2 layers, let me just get the sample here for you to see, 2 layers of the ultra-high molecular weight polyethylene unidirectional, 4 layers of the ultra-high molecular weight polyethylene unidirectional plastic sheet, loosely bonded, so it's not bonded at all, it's just loose layers. The penetration depth was 1.8 centimeters. So a significant drop off there, as you would expect. However, I'm hoping that you can actually see what this looks like, but there are quite sharp edges to this impact point. Now, that's something I want you to remember for later samples when I show them to you. Next, I tested 4 layers of ultra-high molecular weight polyethylene unidirectional plastic sheet bonded with straight silicon adhesive, and that's what that test looked like afterwards, or at least a sample looked like afterwards. And you will also notice that the edges are slightly more rounded than the very sharp edges that you see on the impact point without any bonding. Okay, I might have to edit out or at least put a little disclaimer in, because I think I might have said that the previous test piece had, so the one bonded with silicon had a 1.6 centimeter depth. It didn't. It was actually 1.8. So it was the depth was the same as the unbonded fabric, or the unbonded plastic sheet. So sorry about that, but I'll just make sure I have a little edit or little note at that section. I'm getting old. But this sheet outperformed those two significantly by 2 millimeters. It was a backface signature depth of 1.6 centimeters instead of 1.8. And you'll see that the impact point looks significantly different from the other two. So if I compare it with the silicon there, and then with the unbonded sheets, it's far more rounded. You can't actually even see the edges of that bar anymore. The other thing to note, which is also extremely interesting and very encouraging, is the creases in the unidirectional plastic sheet. This is indicative of a much larger surface area of this material, or at least area of this material, that has been engaged in softening this blow. So in other words, there's a lot more energy that's been dispersed over a wider area here than in the silicon. You can actually see in the silicon, it's a diameter around about there. So it doesn't engage. A lot of the material here is essentially dead to that, that impact. It isn't engaged to try and prevent that impact, whereas here, most of that material is actually engaged in preventing that impact from penetrating further. So this is extremely interesting, and actually the most compelling of the test pieces. Now, I did do a couple of other tests with the Salmon Snot, mixing in a couple of secret sauce ingredients. Their performances were actually not as good in terms of penetration depth, but I think at least one of them, this one, suffered because it was struck right on the edge, and you can see it there. However, both of them exhibited the same phenomenon of massive engagement of that material. You can see it more clearly here. Massive engagement of this armor sheet to prevent that penetration, and very much softened impact edges at the point of impact. You can see it in all three of them. So this stuff is behaving, or at least I believe that it's behaving fundamentally differently to just the plain silicon bonding. Very interesting. Now, I did do another set of tests as well, and I'll really just discuss this one. I made a test piece out of I actually did a bit of reading of some scientific papers on various types of shear stiffening elastomers, and I made one. It's also a silicon-based shear stiffening elastomer with a mix of silicon adhesive and silicon oil. However, this performance was not stellar, and actually was worse. The performance was worse. Now, I must also admit that it did also hit on the side of the test piece, so it was a little bit unfair, but it was significantly worse than just the silicon on its own. So this didn't behave in a way that I would have expected, would have wanted a shear stiffening elastomer to behave. So this one, I'm not going to give the time of day to. Yeah, I'm not going to do any further tests with this, but I think that these samples, in particular the straight Salmon Snot sample, is very promising indeed. This is an extremely promising result. Now, can this be improved? I don't know. It'd be interesting to experiment with perhaps changing its chemistry somehow or other, or like using a different arrangement, that kind of thing. But this is outperforming, at least as it is here, with all the caveats that I've mentioned before. Of course, it is significantly outperforming just the straight silicon bonded unidirectional plastic sheet. So yeah, I think quite an interesting result for the video. So in conclusion, incorporating a shear stiffening elastomer in between the layers of ultra-high molecular weight polyethylene UD plastic sheet did seem to provide a reduction in backface signature by approximately 10%. Now, this may not seem like much to those of you who are not tech priests of the Adeptus Mechanicus, but this is merely a prototype and a proof of concept. In the great scheme of things, this is in fact quite a big improvement over unbonded sheets and sheets bonded simply with silicon, given the circumstances of its construction. There's likely a lot of potential for this design to be considerably improved. It could be further developed and tweaked by altering the chemistry a bit, or even changing some of the components and arrangements. Ultimately, the system would also have to be tested using the stabby pendulum setup to see if it prevents or reduces bunching up of the sheets and point blunt force trauma. I'll see about developing the system further and testing it again in some future videos perhaps. But as a proof of concept, I think this is quite a nice place to leave it for now. That yes, it is actually possible to address the problem of point blunt force trauma by making a system like what I tested in the previous video reactive. Well, I hope you enjoyed this video and thank you for watching all the way to the end. I'll see you all again next time and have as I mentioned earlier, have a great Christmas and New Year. Cheers.